Hi everyone, and if you're completely confused by everything that's going on inside of AI at the moment, then this is a video for you, because we're going to break down exactly what the modern AI system is, how it all works, and we're going to do that by creating our very own chatbot from scratch. And I'm going to help guide you through all the major components. We're going to decipher all of the sort of terminology that's used and really help you understand exactly what the reality is of an AI system. If you don't know who I am, my name is Gareth Davis. I'm the founder of Neural Aspect, and I've been creating modern AI commercial software for the last 8 years, and more broadly I've been involved in cloud software engineering now for almost 30 years. And I think that one of the big issues that we have today is that I don't think I've ever known such a period of rapid technological innovation. And AI, it's only been 2.5 years since ChatGPT kind of burst on the scene, but the advancements haven't really abated at all. If anything, if anything, it's getting faster. And it's not just in the technological sphere, but it also affects marketing and the marketing messaging. We see things that have come up from agentic systems through to generative AI, what was previously called sort of deep learning and things like this, new words for new terms. And I think that creates some confusion as to exactly what is important and what people should be paying attention to. And then, of course, there's a whole bunch of commercial pressure. Companies are being urged to adopt AI as quickly as possible or risk being left behind and put out of business by competitors. But at the same time, we don't know who to trust necessarily. I've spoken with various marketing leaders over the last few months, and the message I'm getting from them is that they are getting bombarded with messages from all sorts of new vendors, and the whole scene sort of changes every few months, and so they're not sure that the vendor that they're going to talk to today is even going to be around in 6 months' time. And it's not just vendors, it's the same sort of thing with professional consultants. As everybody now tries to make themselves be sort of an AI expert. Exactly who can you trust? I wouldn't be surprised if you're there thinking, I don't really know where to start with an AI program, or if I should be starting with an AI program. I don't really understand what the risks are. I don't understand what the potential benefits are to my organization. I don't know, what I can expect from implementing an AI system. How long is it going to take? What do I expect the results to be? What do I expect the impact to be on my workforce? And so there's an awful lot to take in, and there's quite a lot to navigate. And of course, against all of this, we have the backdrop of scary media stories which are projecting that for a lot of AI projects that are being implemented today, that a lot of them fail for various reasons. And at the same time, other industry experts coming out and saying, well, AI is going to take your job over the course of the next couple of years. You need to start making adaptations in your professional life to make sure that you are AI enabled, or again, you're going to be falling behind. We all have now a whole new selection of words and technologies, and deciphering these is not always straightforward. Sometimes, marketing experts like to come up with new phrases for old things. So we have things like vector databases and RAG and fine-tuning. We have large language models. And so, really what we're going to do today is to try and decipher all of this. And we're going to do it by creating our very own little chatbot, which is going to be built from scratch using about maybe it's a bit more than this, about 170 lines of code. It just uses maths. And that's it. It's just maths. And the other thing that we're going to do is demonstrate that it's just maths by using Google Sheets to get the same answers. So if you can do it inside of Google Sheets, hopefully you'll believe me that this is just maths, because I don't think there's anything too magical about the power of Google Sheet functions. So what we're going to be covering today is we're going to take a look at exactly what AI is. What do we mean by AI today? We're going to look at what it is that we're building. We're going to talk about what we mean by a language model, and then we're going to go through the steps of what it takes to put information into the system itself, and how that data is processed and what it takes to produce some sort of output. We're going to then talk about how we train these systems, and then we're going to sort of come back to it and compare the thing that we have created here with the wider, broader, more powerful models that we have on the market, so the likes of Claude and ChatGPT and that sort of stuff. And then finally we'll touch on why this should matter to you. But first off, before we do any of that, I just want to come to our actual chatbot and show you exactly what it is that we're going to be building. Okay, so here it is in all its glory. It's a character-based RNN, and we'll go into exactly what that means in a little bit, but hopefully you'll recognize this as being a fairly sort of familiar user interface that's a bit like ChatGPT. We have responses from our system that appear here, and we can type in some words down here. Now, this is not going to get you your multi-billion-dollar new startup off the ground. This is about as simple and as possible of a machine learning system that you can make to do any sort of language-based task. And so when we put in our prompts into this system, don't get too excited by the output that it's going to give us. If we're lucky, we're going to get a few words in English. If we're really lucky, then we'll probably get a sentence or two that we can understand. So let's just put in a couple of words to get it going, and then we can see, okay, so my company, a something, and then a whole bunch of words. Difference between AI and machine learning. I just needed probably and commercially successful AI software. The point I want to make is this. So, there's sort of a mix of different things here. Some words aren't quite right. Some words are right, and we get the old passage of text that actually does sort of make sense. So I hope you will agree with me that what's being produced here is a bit more than just some monkey tapping on a keyboard and hoping to recreate the likes of the works of Shakespeare. It's not just random stuff. It actually does have some structure and some meaning to it. And so with that, let's jump back to where we were. So what do we mean actually by AI today? Because I was kind of thinking, I've been in this situation a few times before where something's gone wrong with my car and I've taken it along to the garage, and the guy that's at the garage kind of looks at the engine and he kind of goes, yeah. And then as soon as he does that, I know instantly that it's going to be an expensive day, and whatever's wrong with the car, he's going to tell me that it's going to cost a lot of money to fix. And the problem is I don't really have a huge amount of knowledge about cars, and so I don't really feel like I'm qualified to challenge my mechanic on whatever it is he tells me. And if he does tell me something about it, probably I'm not going to understand what he means in terms of the bits of the engine that he's actually describing. So for me, I've always thought, well, it would be nice to actually have a bit of a better knowledge of what actually makes the car work, and how does the clutch kind of work with everything else. And in that way, if I have some basic knowledge, then at least when I go into a garage and there's something wrong with my car, then I'll be able to have a fairly decent discussion with them about what the size of the problem is and what the potential solutions are. I should have a better understanding about whether I'm being ripped off or not, and if I need to go elsewhere. And then finally, I should have a bit of a better understanding about what I need to do to look after the car a little bit better, how I can drive it a bit better, which so that it requires less maintenance. And so what I really wanted to do with this was to provide that sort of equivalent, but for AI, really to give you some sort of sense of, right, these are the major components that kind of work, that make up an AI system. This is how they all kind of work together. And this is what their tasks are. And as a result of that, I would hope that you would therefore be better positioned to have more meaningful discussions with AI consultants that you might be thinking about working with. You'd understand a bit better about whether they know actually something about the subject or not, and whether you're getting ripped off. And it should, I think, give you a better sense of where you can use AI within your organization, what sort of use cases, what the potential risks are, what it's going to be good at, what it's not going to be so good at, and things like that. And to start off, I just want to set the scene and say that for the most part, all AI systems that we have seen emerge since ChatGPT are based on one concept, and that concept is the neural network. It's also called deep learning, by the way. And so about 12 or 13 years ago, researchers figured out that there was a way to make neural networks actually something that had some sort of commercial value with it. Before that, neural networks had been around for an awfully long time, but nobody had really made them work in a way that was actually carried any sort of value. And so when they discovered this, they thought, well, it needs a new name, or their marketeers saw it needs a new name. We need to rebrand it. It needs a nice new facelift. So I tell you what, we're not going to use the word neural network anymore. We're now going to call it deep learning. But effectively, if you see the word deep learning, you can also think neural network and vice versa. The two terms are synonymous with each other. And the other thing that I would say is that it doesn't really matter what it is that you're looking at today, whether it's predictive AI, whether it's generative AI, whether it's agentic AI, whether it's something that produces an image for you based off of a prompt like you might get with Midjourney, whether it's something that is going to produce speech for you, text to speech, you give it some sort of transcript or something and it's going to produce you a voice file, or vice versa, where you're transcribing meeting calls, or whether it's going to do deep research for you as you have in things like Perplexity, or even ChatGPT, or their reasoning models and all of that sort of stuff, then all of them are based on a neural network. And so if you can understand sort of how a neural network sort of works and the process that it goes to develop its intelligence, then you will have an understanding of pretty much all of the modern AI systems that we have on the market available to us today. What exactly is it that we're going to be building today? Well, we said it's a language model. So what's a language model? First off, a language model is an AI system that learns how to understand and reproduce text. And the language model that we're going to create today is actually taken from a piece of code that was created by the rather attractive chap at the top of this slide, and his name is Andre Karpathy. And if you don't know who Andre Karpathy is, then he's the man that coined the term vibe coding only a few months ago. But before that, he was also, I think, head of AI at Tesla. For a long time, he was involved in OpenAI. Before that, he was a lecturer at Stanford University delivering their CS231 computer vision course, which was fantastic. By the way, you can still find those lectures on YouTube. And nowadays, he runs his own channel on YouTube providing educational content in the field of AI, of course. So he created this little program several years ago, and I have sort of tweaked it just a tiny bit to use what's called a deep learning framework. And a deep learning framework is a piece of software that is used to create sort of modern AI systems today. And there is a very good chance that if you are using AI in any form, then the software on which that AI is based would have used PyTorch. very, very good chance most of the research today is also done using PyTorch. And so that's the system that we're going to create. We're going to use the code, and we're going to use what's called a developer tool called an IDE to step through this code. And that's going to enable us to see exactly what the program is doing at any one point. And I'm going to be your tour guide, right? I'm going to be your tour guide, and I'm going to be pointing out the highlights along the way, the scenes to be looking at. And we're going to figure out exactly what it is that's going on inside of our AI system. And to prove to ourselves that there is nothing too scary going on, we're going to show that for parts of this system that you can reproduce the same thing inside of a Google Sheet. So there's no magic, there's no pixies or anything like that sort of wandering around, magically making up letters for us. We're going to prove for ourselves that it's literally just maths. So task 1, we need to train our neural network. So the neural network sits at the core of our AI system. And it's the thing that has the brains to it. It's the thing that has the intelligence to it. So the thing about neural networks is they're not born with any sort of intelligence. We have to create that intelligence. They have to learn it by training. So we have to train our system in the art of writing text, in the art of understanding text. And so how do we actually do that? Well, we find some text, and then we give our neural network training samples, and we'll come on to exactly what that means. We'll give it training samples, which is just basically examples of text, and then we will ask our neural network to make a prediction for each sequence of text, what it thinks the next character is going to be in any given sequence that we give it. And then we will score how well it has made its prediction by comparing it to the ground truth, to actually what we know is the actual character that comes next. And then based off of that, we can then do some funny things with the actual internals of the model that we'll come on to, and in the hope that the next time it's presented with the same piece of text, it's going to do just a tiny bit better. The first thing we need to do is actually find our piece of text. And the piece of text that we're going to use is just a snippet from one of my blog posts. You can find it up on my website, and it's just a paragraph of text. We'll take a quick look at that right now. Okie dokie, so here we are. This is our IDE. This one's called Cursor, but there's plenty of other IDEs out there. Basically, it is a developer tool that we use to write pieces of software. And in the middle here, we have our actual program itself, and the program executes from top to bottom. There is a list of numbers down the left-hand side. These are all line numbers, and so if I scroll down to the very bottom, we will see, okay, so look, there we go. 171 lines of code that we have in this particular program. This is the program which basically I have tweaked from Andrej Karpathy's original. The important thing about this type of tool is that I can put in these things called check marks, these little red dots. And what this does is it enables me to start the program, and the software will stop its execution when it reaches one of these dots. And at that point, we can then see exactly what the program is doing and what it's got in its memory. And that's exactly what we're going to start doing right now. So we are going to run this program. It's just starting up. And so here we go. It's reached this point here. And just this line loads in our data. And so this is the paragraph that we're going to use for our core piece of text. And this is just loaded in from this text file. And so given our data, the very next thing we really need to do is we need to create a list of unique characters from our training set. And so what I mean by that is there may be letters that are used multiple times in our training set, but actually what will be very convenient for us, for reasons that will become apparent, is we really kind of need a vocabulary that we're going to use to make our predictions. And this is exactly what this line does here. So if I just mouse over, we can see at the top here that there are various characters. So they're across not all alphanumeric. We've got sort of characters for cursors, one for commas, one for apostrophes. Then we have numerical number 0, 1, 2, 7, colon, A, C, D. So there we go. These are the unique characters from which we are going to make our predictions. Now we must move on quickly. So we have in total, I think you might be able to see down at the bottom here. So our data paragraph consists of 1,428 characters, and in that there are contained 48 unique characters. And then we have two very important lines, and this is part of what's called tokenization, which may be a term that you've come across before. What this is we need to convert our text into a number, because neural networks do not understand text. They need to work with numbers. And this is a step towards that process. And what it is that we are doing is effectively we are creating a translation which enables us to convert any piece of text into a numerical number. And we do that when we want to put information into our neural network. But then, of course, the outputs that we get from our neural network, the predictions of the next character, they are going to be supplied to us as numbers as well. So we then need to do the same thing in reverse to convert those numbers back into text so that we can actually understand it when we display it on the screen. And that is exactly what these two things are doing right here. And effectively, what we're doing here is just creating a lookup table that says, if you have a certain type of character, then you must assign it this particular index numerical value. And just to make this absolutely clear, we'll take a look at what this means inside of our Google spreadsheet. Inside of our Google sheet that we have, I've created a number of different tabs, and we'll come on to each of these in turn. The one that we're currently looking at is the vocabulary. And so what we have here is a column which represents our character. And so we said there were 48 of them, so they start on 2. And we can come down and look, here's all the sort of letters, capital letters of course, and then lowercase letters are treated differently. And then we have a few numbers in here as well. Now, of course, it is only picking out the unique characters from that passage of text. So we don't expect in this case us to have a complete set of all alphanumeric characters. And now we have a second column next to it, which gives us our index values that we're going to assign to each of these characters. And basically I have just copied and pasted it from those variables that we're just looking at inside of our program. But the net result is that we can now go on to a separate sheet called input. I have just put in what's called a VLOOKUP table, a VLOOKUP formula rather, and that will look at the character that we have in this grey box, and it will go and look up from that vocabulary column what its corresponding index is. So let's just come and put in a letter. So D, for example. So D, it says, is index number 12. Now you may be thinking to yourself, now Gareth, what on earth is going on here? Why have you got this big sort of long list of zeros in green and this one in red? Well, having said that machine learning, or rather neural networks, only deal with numbers, that's true, but the index number that we give it actually isn't good enough. What we have to do is actually convert it into something that the neural network can understand and work with a little bit better, because if you think about it, the numbers that we just give it, those index values, don't really have any sort of meaning. Why should D be given 12 and A be given whatever it was? It doesn't really have any sort of structure to it. And so what we try to do to compensate for that is to convert those index values into this thing called a one-hot encoded vector. Now, most modern systems these days don't kind of use this one hot idea, but it's a simple thing to get your head around, and this is what Andre coded into his program, and so this is what we're going to use. But the general idea behind it is that it's a list of numbers, and there are as many numbers in here as there are items in your vocabulary. So I think we said that there were 48 in ours, and they are all zero apart from the number whose position is at the value of the index, in which case its value is 1. So if we count along from here, and bearing in mind that we're all computer scientists and for some reason we don't count from 1, we count from 0. So the very first number you have to say is 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So position 12 is a 1, which is exactly what you want. So we can change our letters and we will get a completely different series of numbers, a completely different one-hot encoded vector, and it is actually this thing that we put directly into our model. Now then, we have another concept called chunking, and it's not quite chunking because chunking is also used in something called RAG, but I'm not going to get too much into that. Basically, the concept is very similar. And all it really means is we can't put, because of various limitations with the type of system that we're building here, we don't have the ability to put in our paragraph complete into our model. It really wouldn't serve its purpose for us. So what we want to do is we want to split up our paragraph into lots of little sequences, and then we're going to feed those sequences into our neural network, and we're going to ask it to make the predictions that we want for the next character based off these much shorter sequences. So the training process will take the sequences that we've provided. It will take the predictions of each character in that sequence and then compare it to the ground truth. And we know what the ground truth is because the ground truth is just the next character in the sequence of the text that we provided. And so it might be easier for us to actually look at the code to explain this a little bit further. Right, so here we are. We've got our char to x and x to char, which are our mappings, translations rather, to convert characters into numbers and numbers into characters. And then we're going to sort of step through much of this. Right, so seek length. This is what's called a hyperparameter. Basically, it's a value that we set to specify how long that little snippet of text is going to be that we're going to put into our model. So this says here that we're only going from our training material at paragraph of text, we're going to take little snippets that are 25 characters long, and then we're going to ask the model to make predictions for each of those characters that we are going to supply it with. Right, so we've just fast forwarded onto the sort of relevant piece of code that we're looking for here. And having created our little piece of code that does the conversions from characters into indexes and indexes into characters, we're now in a position to actually process our data. What this inputs line does is it says, okay, we're going to use our starting paragraph. We're going to use our paragraph. And from this paragraph, we're going to take the first 25 characters. And then for each character in that section, that 25, we're going to convert into its corresponding index. And then we can then use that as our input into our model after we've gone through this one hot encoding that I'll show you. But then we have underneath that this targets variable, and the targets is just another way of saying this is the ground truth. So whatever our model predicts as being the next character from these inputs, we are then going to compare to the ground truth, this targets. And so what's this target? Well, it is literally just the next character. So in other words, what this does is this creates a snippet of 25 characters, but instead of starting that snippet from the first character of our data, we're going to start it at the second character of our data. And then, of course, we then need to convert that character into its corresponding index so we can do a direct comparison. And so if we now move forward, we can compare what these lists consist of. So inputs is this list of numbers. So 25 in total, beginning with 0. Then 22, 30, 27. Now targets, conversely, starts at 22. And then it goes on to 30 and 27 and so on and so forth. So what this is saying is, if we put this number 0 into our neural network, then we would hope that it would predict for us the next character of 22. And whatever it does produce for us, we can measure how good its prediction is based off of this list of targets. And similarly, when we put 22 in, then we expect to get 30 out. When we put 30 in, we expect to get 27 out, and so on and so forth. And it will do that for the entirety of this sequence. We're going to move on now to the actual model itself. Now, so this is basically the hardest bit of the entire video. If you can get through this, then we'll be on the home straight. What we refer to as the neural network, I also talk about as being models. It's basically, that's the core brain. And as I said, it starts off life as being something which has no intelligence whatsoever. And it is through this training process that we create this sort of notion of intelligence. But effectively, what we're dealing with is a mathematical functions, or rather a series of mathematical functions. And those mathematical functions are guided by the values of these things that are called weights. And weights are just numbers. And those numbers start off being random. In fact, they are initialized to be completely random things. And the training process makes those numbers less random and more suited, so that when those numbers are used within these mathematical functions, that they produce the output that we're looking for in order to solve the particular task that we want to train our model on. Now, I know this sounds somewhat confusing, but the important thing is here is that effectively the magic of it all happens because of the numbers, the specific values that we assign to these weights. Without that, this whole neural network has no ability whatsoever. That's the magic bit to it. And the rest of it is just basically running through some maths. We're just adding things together, we're multiplying some things together. It's literally something you can put in your calculator, or as we will see, inside of a Google Sheet. And so these are the two concepts that are kind of really most key. The fact that we have our weights, these are the things that we learn, and then we have a series of mathematical functions, which I guess you can think of as being, some people might refer to that as being the algorithm or the architecture of the model. And you need both of those things together in order to give you a system that actually has intelligence. And so we're going to look now at how those two things are created, and then we'll move on. We're sort of partway through this code here. We're going to move on. So first off, here is our input of tokens that we have created, our 25 tokens. And what this line does here is it says, okay, we're going to treat each of these tokens in sequence individually. And so the first element of our tokens, the first number in our tokens is 0. So we're going to handle 0 first. So t is going to be assigned with the value 0. And what we're doing here is we are creating our one hot vector from our index of 0. So xst is our one hot vector. And so if I put this up on my screen here. Now remember, the first index value from inputs was 0, so therefore we would expect the first element of our one hot vector to be 1, if that makes sense, because it's in position 0. So the 1, because it was a vector of 0, is in position 0. So now we have our one hot vector. Then we have our next two lines. And these two lines, that is our neural network architecture. That's all there is to it. Now there's going to be some things in here which are unfamiliar to you, and that's okay because we'll figure this out. But what this is saying is we have a thing here called wxh, and we have this @ sign, and we're going to use this wxh to perform a mathematical function called a matrix multiplication. That's what this @ sign denotes, with our input, with our one hot vector that we've just created. So what does this wxh mean? What is this? Where does this come from? Well, we actually skipped over this earlier, but we created this thing. In fact, we created 5 variables, which are our weights that we need to use within our neural network architecture. And so wxh is literally just a big list of numbers. There we go. We don't show them all there, but we've got a fairly good understanding of what it is. And it's exactly the same for these other ones. So whh, big list of numbers. why, big list of numbers. And as I said, when the model is first created, before it's trained, these numbers are completely random. Other things that start with B, they're called biases, and we initialize them as zeros. So we expect BH to be a big list of zeros, and we would expect BY to be a big list of zeros. So there we go. So these are our weights. These are the things that we are going to learn throughout our training process. And so we update these as we learn. And we use these inside of our neural network architecture. And so to be precise about what we were saying earlier, we have our table wxh of numbers, which we're then going to perform a matrix multiplication operation with our one hot coded vector. The result of that, we're then going to add to another set of weights called hh, which is going to have a matrix multiplication with this hs term, which I haven't discussed yet. And to be honest, I'm just going to gloss over it. But effectively, it is just another number. Basically, you can think of it as being like memory within our network, so that you can remember what characters came before it. And then whatever that result is, we then add it to this bias term, which we said was initialized with zeros, so that's all just zeros. And then we're going to perform this torch tanh function. And that's just a trigonometric function called hyperbolic tan, and basically that just squishes the value between -1 and 1, and then we're going to assign that calculation to this hst variable, and then finally we'll skip to the next line. Then finally, we're going to take that value, hst, and perform another matrix multiplication operation with the final set of weights that we have, why, add on the bias for that, which is also 0, and that's going to give us YST. Now YST is the prediction that we are going to use for our next character. It is in the format of something called a logit, and that means that it can have any sort of value, but having any sort of value for us doesn't really help us. What we want to be able to do is to get it into ultimately the actual text character that we want to know. And in order to do that, the way that we do that kind of operation is we first convert our output here, which is just a big list of numbers, YST, which is our big list of numbers. And if I say YST.shape, it should tell us how many numbers there are in here. And there are 48 of them. And if you remember, the vocabulary that we are using has 48 characters. And so what this means is that each one of these numbers can represent how likely each character in our vocabulary is to be the next character. But it's in this logit form. So the thing that we want to really do with it is to convert this into probabilities, to give us how, a probability of each character. And that's what this next line does. We actually use a mathematical function called an exponential, and that just forces our numbers all to be positive, and then we then divide that by the sum of those exponential values, so that basically it becomes like a probability, like a percentage type of thing. And so if we just move over, then we should see, I hope, a set of numbers. So here we go. So they're all positive. They're all less than 1. So hopefully, with a bit of imagination, you can think that they are probabilities. Now, just to reinforce this a bit further, we're going to look at our Google Sheet, and I will try and walk you through what we're doing there. Right. So the numbers themselves are going to be slightly different, because I've actually loaded into this the values of the weights after the model has been trained. But effectively, I've just copy pasted those numbers from each of those variables into this sheet here. So you can see big list, and here's another big list, and here's another big list. These are one of the biases that we've learned. That's another one of the biases that we learned. So these are the weights, and the 2 single columns are the biases. Remember, this is our input. This is our one hot encoded vector. And so this hidden sheet is basically where all of our calculations happen. This funny H thing that I sort of said was memory. When we first use it, we always set that value to be 0. So that's 0. You might remember that we had in our architecture the mathematical functions, the first of which was WXH at much multiplication with our one hot input. And so this is exactly what this does, and we have a formula here for it. So mmult, matrix multiplication, WXH, and then transpose. I have to convert that row into a column so that it can actually perform the matrix multiplication properly, but we're just using this one hot input. Okay, so that's that value. Then we have our second value that includes our H, and funnily enough, because everything here is 0, when we do matrix multiplication, anything to multiply by 0 is also 0. So these are all zeros. And then this column here takes the value of our matrix multiplication with our inputs, adds it to the value of our hidden state with the weights with those weights, and then adds on our bias terms, which we had a look in our first tab here, and that gives us this set of values. So basically we're just saying add this column and this column together, and then this BH term, which we said is in this weights tab, and then this array formula just says, rather than just put it in this one cell, then just make a big list of it. And then once we've done that, then we can create our tan-h function. So as I said, this is just a trigonometric function. So this just says, okay, whatever, just do tan-h of this value here. And that is gives us our new hidden state. So effectively, this gives us our h. So that's the first line of our code done. And then if I come to outputs, our outputs now say, right, we want to do a matrix multiplication of the thing that we just created, of the thing that we just calculated, and do a matrix multiplication of that with our final set of weights that we have available to us from this first tab. And that produces this output in column A. And then we want to add on our last bias term. So this just says, okay, the thing that we just calculated, matrix multiplication with our last weights, then add on our bias term. That's it, just maths. And that gives us our logits. And then convert these into probabilities. And the way that we do that is we take the exponent of each of these logits, which is what this is. Just again, another Excel sheet, Google Sheet formula. And then after we've done that, we can have a final column which says, okay, we just divide the value of these exponents of logits by the sum of this column to give us those probabilities. Okay, I hope you're still with me, because this now puts us in a position where we can start making predictions. So we have a set of probabilities, as we said earlier, one for each character in our vocabulary. And we have a choice here, right, about what we can do. And the choice is, we could either say, you know what we're going to do is we're going to take the most likely character from these probabilities. So we're going to find the character, or rather we're going to find the index on this where the probability is the highest. And we're going to say that that is our prediction. And that's what this cell does here with this rather fancy bit of formula that I needed a bit of ChatGPT help with. But effectively what it does is it just looks down this column, picks out the highest number, and tells me what its position is, counting from 0, 1, 2, 3 up here. So this says the index at 43. So what's that going to be? Line 44, I suppose. Yeah, so this line here, basically that's 10.5%. So this is saying 10.5% likely that the character at this index 43, is the next character. And so this cell here just does a lookup for this index. So this looks up in our vocabulary and it says, okay, so index 43 is actually character U. So that's our prediction. Now, there is another way of doing it, and the other way of doing it kind of relates to something called temperature. So the other way of doing it is to say, you know what, we have our probabilities here, and what we're going to do is we're going to put our probabilities onto a sort of big wheel of fortune type thing. And each segment of your wheel that you have, its size is going to be proportional to the probability of the character that represents. And so we have a segment for each character in our vocabulary, and then the size of the segment is related to how likely that character is going to be the next character that we're going to predict. So we create our big wheel of fortune, and then we spin it. Whichever segment it lands on is going to be our prediction. And so with that, you can imagine that you would not always get the same answer every time you spin the wheel. There's a good chance that you'll get the most likely answer, but the character with the biggest probability, but not always. And as it turns out, having this sort of uncertainty, randomness to it, enables the models in the sort of generative space to be to work much more effectively. Models that operate with what's called a cooler temperature, a temperature of 0, place far more weight on this wheel of fortune, give far bigger slices of segments to the characters that are most likely to be the next character. As the temperature increases, these segments become relative to each other sort of more even, until eventually they all occupy sort of the same space, the same size. And therefore, when you spin your wheel of fortune, it's completely random as to the character that you're actually going to get next. And so in this type of situation, where you would want your language model to produce something that is more creative, then having a little bit of temperature to it, a little bit more randomness to it, often creates a better result. Whereas having an AI system that is, say, producing and summarizing like legal documentation or something like that, where you absolutely do not want it to be making stuff up, you want to be running those models on a very low temperature so that the probability is that it's going to select the next character in our case, or the next word, the most likely word that the model actually believes is going to be. So that's that. Right, okay. So we've just been through this sort of sampling exercise. So we've talked about the probability outputs, and we've talked about this idea of temperature and spinning our wheel of fortune. Now we need to talk about the actual training process itself. And I'm not going to go into too much detail here because there's a lot of stuff that's going on. But again, the main idea that I want to try and convey is that we are just using numbers and mathematical operations. So let's just go back into our code again. We've got our outputs, our probabilities for each of the characters that we have in our vocabulary. And this line here, this creates something called the loss. Now, we don't need to go into the details of exactly what this is, but the important bit is it compares the value that we've just predicted with our targets, and it's going to make a numerical calculation of how close our probabilities were to the actual ground truth. To the actual ground truth. So that's the important bit. This is the how do we assess how good the model has actually done at predicting it, and we do it again using maths. Now, once we have that number, we then have to go through a rather laborious process which involves taking something called gradients. Now, we're not going to go too much into what gradients actually are. Effectively, we need to use a mathematical concept called calculus in order to calculate it. But what we are doing is we are looking at our loss, which we can think of as being like an error. And we are seeing for each of the weights that we have in our big sort of tables and our bias terms, we are seeing how that error changes, how that loss varies as we tweak values in those weights. And this happens to be a particularly efficient way of finding values of those weights which get us to a point where our loss reduces and becomes as small as possible. So if you think about it, if the loss is very low, then that must mean that the predictions are very close to our ground truth, which is exactly what we want. And so the way that we do that is through this algorithm of finding these things called gradients. And those gradients apply to each of those weights and those bias terms. And then, once we've gone through and we've calculated our gradients for each of those weights and bias terms, right, so we've now got our loss function here with these gradients. And then we have, this is the important bit down here. Let's move on to that. This is all a bit codey, confusing, but the principle behind it is that we take the parameters for each of our sets of weights and bias terms, and for each of those parameters, let's say that, we then modify it by a value which is determined by these gradient terms and this thing called learning rate. Now, there is a particular algorithm that we're using here called ADAGRAD. Again, the details of it are highly uninteresting to you. But effectively, what this is just saying is that we've figured out the best way to change our weights based off of what the loss was, and therefore we need, so in order to minimize our loss further, in other words, make our prediction better, we need to change each of these weights by some amounts that we have in these gradients, multiplied by this learning rate factor, which is just a variable that we kind of set up front. And so when we go through this process again next time and we give it another training example, then we would hope that that loss term would be slightly better, and our gradients then would repeat that process, and we would then adjust our weights even further and make the loss even lower for the next time round. And we keep on repeating this process time and time and time again. And just for context, I trained this model for, I think, 500,000 loops of doing this in order to give you the output that you were seeing earlier on the screen. And so it does take a long time. But that's it, right? That's basically how a neural network learns. And it doesn't really matter what the task is, whether it's producing text or whether it's producing images, whether it's transcribing or whatever. They will all involve this process of finding gradients from a loss and adjusting the internal parameters based off of the value of those gradients. You know everything for a neural network. Right, so just before we sort of finish up with the code here, I just want to show you what it's like for the whole training process to run through. I think that might give you a better sense of what it's actually doing. And so we're just going to run the program without sort of interrupting it and let it go through this cycle of training. And I just need to find a suitable place in the code. There we go. For us to stop here, this is our first attempt. So the model's not been trained yet. This is our first attempt at making predictions. In other words, it's just producing nonsense, right? This is all just random stuff. So let's bring bring this out. We'll let it run on. And now we can see it's actually sort of going through. There's lots of activity going on. I will pause it just in a moment. Let's just get to, I don't know, around sort of 10,000 iterations. Here we go. So here we are, 10,000 iterations. So it's gone through this whole process 10,000 times now. You can see that it's kind of got the sense of what words are. We've got like the odd word in English that might be, there's a few words, the, to, and. So there's a few words there that kind of make sense, but they're very short. But it's definitely got, a sense of words, sentences. It's got grammar in it. There's full stops and things like that. So let's go on a bit further. And what's our loss? Our loss here is 17. I don't know what our original one was. So we're looking to get better than 17. So I lost down to 14, 13, 12, 11. And maybe we'll let it go to 5 or something like that, and then we'll pause it again. Here we go. So here we are. On the least, also we've got some more words there that kind of make sense. I had lead. That's I stars that. So it's improved. It's definitely improved. Slightly longer words now. And then let it go on just one more time and see how much more of an improvement we can get. Like I said, I needed to run this for about 500,000 iterations before this kind of was producing consistently good output. Right, okay, we'll leave it here. So I've stopped it when now the loss is about 0.9. So it, AI, and or provide, that's a longer word. Were, he, hand, that I needed to know. So sequence of words that kind of made sense when you put them together. To understand what machine learning was, and well, there you go. I mean, that's starting to produce some sort of realistic output, isn't it? So therefore, I mean, I hope you can sort of see just now what that process is. So if we're just doing this loop of making predictions, understanding, calculating that loss, calculating these things called gradients, and then changing those big list tables and numbers that we're calling weights. And we're doing that over and over and over again in a way that we try to lower our loss as much as possible. And so that's it, really. So, of course, what we've created is just something that's incredibly small, incredibly simple. It's not the same as the big ChatGPTs, Claudes, and all the big LLMs that are out on the market today. But the principles on which this is based are still the same. In fact, the principles on which it is trained are still the same. Well, what are the differences? Well, the type of structure, the architecture that we use in our model is something called an RNN, which is called a recurrent neural network. Basically, it just defines the way the actual mathematical functions that we're using. Virtually all large language models today will use a different type of architecture called a transformer. It's not particularly important, but these found that these transformers tend to do a very good job of understanding text. They also do a good job of understanding images and also other domains as well, providing you give them enough information. But what you find is that for these transformers to work is that they need an awful lot of those parameters. So those weights, there's many, many, many more of them. And so whereas we only had sort of a handful of those weights, parameters, the large language models that we have today with us have billions of those parameters. And that's kind of, one of the big differences in terms of how our model compares to what is commercially available. The other thing that I think I touched upon earlier is, rather than using these one-hot vectors, we tend to use nowadays something called embeddings, which is a whole subject on itself. If you like, then like this video, and I'll do another video on embeddings and exactly what they are. But they're a bit more of an efficient way of handling those inputs and into a slightly different vector. Then there is, I'm going to put RLHF here, but effectively what we've done here is we've created what Andrej Karpathy would call a document completer. It doesn't have the same sort of question answer type capability that you would expect from a ChatGPT type thing. So what this thing wants to do is it wants to write documents, it wants to complete documents. And so what you find with the language models, the large language models that we have today, is that there are a couple of additional steps that the training process goes through in order to give it that sort of question and answer type capability. All of the knowledge that they have is acquired during its initial phase of training, which is what we have just gone through. And so that knowledge is obtained effectively by having a data set which, rather than using a single paragraph from one blog, really consumes the entirety of the internet, as much written text as it can get its hands on. And so we've found that in so doing that these models suddenly become extremely powerful and extremely knowledgeable. We don't really yet understand why. It's very difficult for us to interpret how a model arrives at its predictions. What that actual thought process is. We just don't understand it. Anthropic are actively working on this area of interpretability right now, in trying to get some sort of insight into how these large language models work. It's something that has been done on a much smaller scale, but we just don't know fully how these things properly work. So there we go. There's some differences with what we've created and what's currently available on the market today. So hopefully now you should understand what the core sort of idea is with training. You should understand a little bit more about what the things are with temperature, how it's arriving at how it's making its predictions, what the process is to train these models. You should understand a little bit more about some of the terms that are being used: tokens, chunking, vectors, what we mean by parameters or weights. And so I hope that this kind of guided tour has given you sort of a bit of a background as to how these AI systems all sort of come together, and that will put you in a better place to have more meaningful discussions with your vendors, with your AI partners. It will enable you to have a better understanding of where you can use them inside of your organization and things like that. So that's pretty much it for this video. If you like this, then please click on the like button, subscribe, all that sort of stuff. I'll make this Google Sheet available so that you can have a look and a play with it yourself. And if you need any help with your AI programs, then please feel free to reach out to us at Neural Aspect. We'd love to see if we can help you out. And we'll see you in the next video. So thanks very much, and bye for now.